Hi everybody. Well, today we're going to tackle one of the more interesting engineering problems in making the computer that's sitting in front of you. And that's the problem of engineering the memory system. So let me see if I can sort of set up what the engineering problem is we're going to work on here, both this lecture and for the following lecture. So we use a memory system, and we use memories in a couple different places in our block diagram. Here we're showing the main memory on this slide here, where we actually, it's a two-port main memory. We use one of the ports to send over the program counter and get back an instruction, and the other port we use when we're servicing load and store instructions, where we compute a memory address by adding the contents of register A to an offset, and then we send that off to the memory system and get back a piece of data, or in the case of a store we also send over the data. And so one of the two memories that we have in our system is this main memory, and it's basically organized as a billion 32-bit words. So 2 to the 30th words by 32 bits, and it's basically a two-port memory, and then there's also sort of the read and write that happens. Okay, so that's one of our memory systems. The other memory system is the one that is the register file that's built into the CPU data path. That's where we get the two register operands for each instruction, and it has sort of the same organization. It has two read ports and one write port, and it's organized as 32 locations, or 2 to the 5th locations by 32 bits. And they very much work the same in the sense that the reads are combinational and the writes are, I haven't turned on the microphone. They very much work the same. Wow, the voice of God, okay. Thank you. They very much work the same because the reads are combinational and the writes are relative to a clock edge. We have a bunch of technologies available to us, and they sort of vary according to the capacity of the memory that we can build and the latency involved. So the register files that we're dealing with, the latency is measured in tens of picoseconds. They're very expensive to build. That speed is because we're devoting a fair amount of silicon area to getting that. And the fact that they're small also allows them to be fast, because the capacitances involved in the signaling wires are small because they don't have to go very far. At the other end of the spectrum, we go through both static RAMs and DRAMs. I'll say a little bit about the technologies of those in the next couple slides. And as we go up the hierarchy in terms of capacity, we're also going up the hierarchy in terms of latency. And the main memory that we're talking about is built out of this dynamic RAM technology, and I'll explain why it's called dynamic in just a second. And we can get hundreds of megabytes is slightly obsolete. Now we're in the handful of gigabytes range, so 4 gigabytes or 8 gigabytes, something like that is what most of us have. The trouble is the latency is long compared to the length of an instruction. So an instruction might be executing in a nanosecond or so, or half a nanosecond, and yet the cost of going out to memory to fetch a piece of information is on the order of 40 nanoseconds, so 10 times as long, or something on that thing. And you look at that and you sort of go, wait a minute, there's a problem here, Chris. If I have to fetch each instruction from memory, how does that work? How is it I'm able to execute instructions in 1 nanosecond, but part of executing each instruction is fetching it from memory, and that takes 40 nanoseconds. That just seems like a real fly in the ointment, and indeed it is. And in fact, over the last 3 or 4 decades, what's happened is that the speed of our logic has increased as the technology, CMOS technology, has improved, and the capacity of dynamic RAMs has increased as the size of our transistors gets smaller and smaller and smaller, but the latencies in the dynamic memories, which are pretty much controlled by the size of the memory, have not increased dramatically. These are a little better than the first DRAMs that came out, but not by several orders of magnitude, or 3 or 4 orders of magnitude, that we've gotten for processor speeds. So this is a problem. We need to go solve this. And so we're going to sneak up on the answer today. First, I'm going to tell you a little bit about each of these different types of memory technologies, so you at least get a glimpse of what they look like. And then we'll set out to seeing if we can solve this puzzle about how do we make a fast processor that has to access a slow memory. So keep that in your mind as what our goal is today.